Hello, young friends. This is a refresher series for grade 11 physics. It's based on NCERT or CBSE syllabus. In this, the theory concepts are very well explained and a few sample questions are also solved. These are some of the tougher questions in this chapter, taken mostly from NCERT book or few from NCERT exemplar book as well. After this, we consider that you should be ready for directly practicing competitive level questions. The topic of this video is NCERT chapter 4, that is motion in a plane. So let's start the journey. Okay, in this slide we will discuss vector addition and subtraction. Now vector, as you know, is a quantity which has magnitude and direction. So let's look at the figure on the right, which I am pointing now. So there are two vectors, one is vector A, other is vector B, and each has a magnitude and direction. So magnitude is proportional to the length of this vector, and direction is it's pointing in a particular direction. So this is how a vector is represented, showing both magnitude and direction. Now if we have to add these two vectors, the rule is that you put the tail of the second vector touching the head of the first. So this is the head of the first, this is head, and this is the tail of the second. So if you go towards the right, figure on the right, okay. So here A is this vector, again same. B is placed such that the tail of B is touching the head of A, and then and since these vectors, the length of these vectors is proportional to their magnitude, the resultant vector will simply be the line joining the tail of vector A to the head of vector B. It's as simple. And the direction you can see is in this direction. So magnitude is represented by the length of the vector R, resultant vector R, as it is mentioned here, you can see. So you see this is R, this is the resultant vector, it's the addition of A plus B, this vector addition, and its length represents its magnitude, the length represents its magnitude, and the direction is of course in the right direction. So this is how you add vectors. And geometrically you can find the length of this and then you will know the magnitude of this vector. Okay. Similarly, subtraction is similar. So subtraction is what? Let's say, let's look at the line which I'm pointing now. So A minus B, what it actually means is A plus minus B. So if you have minus B and add it to A, you will get the resultant. So here, if you see the figure which I'm trying to point here, there is a vector A. It has a, as we know, its length represents magnitude and the arrow represents direction. And to that you have to add minus B. Now minus B has a direction opposite to B. So if you remember B here, it has a direction on this side. So minus B will have a direction on the other side. So therefore you have a minus B shown here. Again, head meeting the tail. So head of A meeting the tail of B. So this is the head of A meeting the tail of B. So, and then ultimately you have the vector addition diagram, and in that the resultant is shown here on this side. So resultant is A minus B, and that is this vector. This vector shows the resultant. It has a direction which is upwards, and magnitude is the length of this, equivalent to length of this. Okay, and now based on this, let's look at an useful example given also in your NCERT book. It's example 4.1 taken from your NCERT book. how we use vector addition. In this case, we'll be talking of two vectors that are at 90 degrees or right angles. Now, what does the question tell us? So it says rain is falling vertically with the speed of VR. This is what it's naturally rain falls vertically. So this is represented in the diagram, which I'm trying to highlight. So rain is falling vertically. Okay, rain is falling vertically, and there is a wind blowing. Now you see this in the question. Wind is blowing with the speed of VW, V wind, say east to west. That means it's in the horizontal direction. Rain is falling vertically and wind is blowing in a horizontal direction. So let's look at the figure on the right hand side again. So rain is falling vertically and wind is in the horizontal direction towards the left. Okay. So this is what the question tells us. Now assume that this length of this vector represents its magnitude and length of this wind vector represents the magnitude of the wind. Proportional, these lengths are proportional to rain and wind speed or yeah velocity, and then naturally by simply drawing this resultant V, which I am pointing, so we are simply drawing this resultant V which is given here, we get the resultant angle at which raindrops will fall. So raindrops, as you can see, will fall in a slanting way. Raindrops will fall in this slanting way. They will not be straight. Original raindrops are falling like this, but because of the wind, they start falling in a slanting manner. And that is why if a boy is standing in the rain, it is better he inclines the umbrella in that angle. The angle which he has to incline is, if you look again at the diagram which I am trying to point out, there is an angle here. And this angle you can find out simply by trigonometry of this vector diagram. So trigonometry of this vector diagram, what does it tell you? That tan theta, tan of this angle is this VW divided by V rain. So this is what is given here. So tan theta is V wind by V rain, and that is the angle at which boy should hold the umbrella so that he doesn't get wet. Because if he holds above, because he will uh, he will get wet. But if he holds at a slanting position, suppose he held his umbrella like this, so the rain will fall and make him wet, right? But he shouldn't hold like this. He should hold it in this fashion so that rain is stopped by the umbrella. Okay, let's go to the next chapter. Okay, just before I close, I think I forgot to tell you to add here, um, and that is that the magnitude of this um, angled rain, let's say the slanting rain drops, the velocity or the magnitude of this is given by finding the length of the hypotenuse, because this is a right angle triangle, as you can see in this diagram. This is a right angle triangle, so therefore the value or magnitude of the rain velocity, let's say, will be simply as given on the left hand side. I'm going to point it out here. You have to use simply geometric formula for hypotenuse and you'll get the amplitude of the velocity of the rain as well. But of course, in this question, we don't need that. We just need the angle, because the question asked which angle should boy hold the umbrella. So that we found out with tan theta. Okay. So now in this diagram, we continue with our discussion of vector addition and subtraction, but here we try to apply it to the concept of relative velocity. So if you see in this slide, the first item which we are discussing is relative velocity, which I am trying to highlight. And if you remember from your basic motion principles, relative velocity is a difference between the two velocities. So if, for example, velocity of object A is VA and velocity of object B is, let's say, VB, then we say that relative velocity of A with respect to B is VA minus VB. Now, as a point of concept, just remember that when we are talking about relative velocity, we are theoretically assuming that this velocity is of B of item A, assuming B is stationary. This is how we can imagine this relative velocity. That means we consider VB as stationary in our mind, object B, and then we see what is the relative velocity of VA. So it's basically vector difference of VA minus VB, and on the right hand side, let's look at this diagram. We have one vector VA, one vector VB. We have to subtract these two. If you remember from previous slide, we will try to find a vector which is negative to VB, so minus VB is this. Then we'll add VA with this minus VB vector, so that's what we are doing in the figure on the right. If you see this figure, so here if you see VA is kept here as it is, VB is reversed because we have to subtract VB, and therefore we get VA minus VB. Okay, so this is vector subtraction. Now, or let's say relative velocity. Now let's apply this relative velocity. This again is an example taken from your book, but it's an important and useful example to rub the concept and make it more understandable for us. So what does the question tell us? Rain is falling vertically with velocity of VR. Let's always draw a diagram, it makes it easy. So you see here rain is falling vertically. A person rides a cycle with velocity VC. Now it's normal to assume that person riding on the road will his velocity will be at 90 degrees to the rain. So if you see the figure again here, I have drawn the velocity of cyclist in one direction which is at right angles to the rain. Direction is this side, rain is this side. So they are orthogonal to each other. Now we need to find, okay, the question is, at what direction should he hold the umbrella? So what we need to know is what is the relative velocity of rain with respect to cyclist. Relative velocity of rain with respect to cyclist. If we know the direction of that velocity, we can know at what direction or what angle should the cyclist hold his umbrella. So we know the relative velocity is a difference between the two velocities. That means velocity of rain minus velocity of cyclist. So what we need is relative velocity of rain with respect to cyclist. So it will be VR minus VC. Now we'll simply put this in the vector diagram. So if you see rain was here and we put the rain vertical still here. V cyclist was going in this direction, but we have to take its negative value. So V cyclist will be this. So it is this value here. And so we add, so again now going directly to the figure totally on the right hand side. So we add this with the negative of this and we get a resultant which is this, right? VR minus VC. Our question is the angle at which the cyclist should hold the umbrella. That means we need the angle of the resultant velocity of the rain. So if you see, this is the resultant velocity, right? And the angle you can find out using trigonometry. So this angle theta, which is the of the resultant raindrops with respect to cyclist, is at an angle of theta, and that theta is this VC divided by VR. Of course, direction doesn't matter because here we are trying to find the angle. So it will be magnitude of VC divided by magnitude of VR. So that's what is given here, and that is the angle at which cyclist should hold his umbrella. Okay. In this slide, we continue discussion on the topic of vector addition and subtraction. Now, in the previous two examples that we saw in previous slides, we found vectors were at right angles to each other. But that's not a general case. In a general case, the two vectors may not be at right angles to each other. They could be acute angle or an obtuse angle. So here we are going to consider a general case, and let's look at this figure on the right hand side. There are two vectors A and B, and as you can see, they are not at right angles. Let's say they are at an angle of theta degrees, and that is what is plotted also in a figure on the right hand side. Now let's say we have to add these two vectors. So what we will do, we will use the same principle. So now look at this figure carefully. This is vector A, right? Same direction, same magnitude. Then let's put the other vector in the same fashion that we did in previous theory. That is, we put this vector here. As you can see, this is vector B. The tail of vector V is touching the head of vector A. And therefore, with all this summing up, we get a resultant vector which I am trying to highlight here. This R is the resultant vector, which is the diagonal in a way of this parallelogram. So the figure we see here is a parallelogram in a way. So this is vector A, as I said. This you can consider as vector B, and this is the resultant. Now let's draw the parallelogram to make it easy for us to geometrically calculate the value of R, the resultant, and its angle with respect to, let's say, A. So what we need to find out is the magnitude of this R and this angle which this R is making with A. Okay, this view what we'll find out. So this angle is alpha, and R of course is the magnitude. Now you have to remember these formulas on the left hand side, and I am trying to highlight them. So the magnitude of the resultant is given by this formula. Square of magnitude of A, square of magnitude of B, and twice AB into cos theta. Cos theta was our, just showing you again on the right hand side, cos theta was our angle between the two, and it's also given here in this figure. Okay, so with this you get this you have to remember. Then let's look at the third formula here, the one which I'm pointing here. That gives you alpha, the angle of resultant with respect to A. So that is found out directly by this. That is found out directly by this formula. So which is given here, tan alpha is equal to this, the angle of the resultant. Then let's look at a question based on this. Okay, the question reads here, and which I marked here, is a motorboat is going towards north at this velocity of VB, and the water current has a velocity of VW, and it is in a different direction. It is 60 degrees east to north. So always it's good to, as I say, draw a diagram, a clear, neat diagram. Maybe this not so neat, so maybe you can make a bigger one so that you can show, you can put all your parameters here. So one is motorboat is racing towards north at VB. North is here in the diagram, if you see in this diagram, and VB is therefore in the same direction as the north. Okay, so this we have plotted correctly. Then the next item in the question is 60 degrees east of north, you have the water velocity. Okay, east of north. So here you see, east of south, I'm sorry, east of south, and this is east. This east, this is south. So east of south is this direction, and 60 degrees is shown here. So let me make it clear now. So this is the angle which we are talking about is 60 degrees and also written there. So that is the velocity of water. Assume that this diagram is drawn from a drone or from the top, looking at the boat which is trying to go in the north direction, and water velocity is in this direction. So we have to find the resultant direction in which the boat will go. So naturally you need the resultant, and resultant means what? Adding the two velocities. Adding the two velocities in this case, since they are not at right angles, we will use the parallelogram geometry. If you go to the top, the first half of this slide, we talked of geometry of a parallelogram in case the two vectors are not at right angles, and the resultant is this one. This is the magnitude of the resultant, and the angle is this one. So simply you have to apply these formulas. You know the amplitude of vector A is amplitude of vector A, as you know, is already given as VB. Amplitude of vector B is already given as VW. So you have to simply apply the formulas here. This is amplitude A square, amplitude B square, 2AB, and cos theta. You already know cos theta is what? Cos theta is the angle between VB, which is in this direction, and V water, boat versus water, and we already know this is given as 60 degrees. So this is 180 minus 60 degrees equal to 120 degrees. So simply you have to apply, and this is theta, this theta. So simply you have to apply this equation or this equation and get your answer. Okay. The topic of this slide is projectile motion. So it's a bit different than the previous slides. In this case, an object is thrown upwards. So let's look at this diagram, which I'm pointing here. This is the diagram we are talking about. So here, if you assume that a object is being thrown with velocity v0 at an angle to from the horizontal. So the angle, if you see, is theta 0. It's marked there as theta 0. So this is all about an object being thrown at a angle of theta 0 upwards, and as you can imagine, it will take a path as shown here in this diagram. This is the path that it will take. Now if you look closely at this path, there is an impact of gravity. So you can imagine there is a force of gravity which will be acting in a direction opposite to the vertical climb of the object. Now let's look from a vector perspective. So again, back to this diagram, you see this velocity v0. It will have two components, orthogonal components. One is v0 sine theta in y direction, v0 sine theta, and v0 cos theta in x direction. So we have these two components. So any velocity can be split into its components, orthogonal components, which will create this final velocity. And just to remind you of the concept of vector, so as you know, a resultant vector can be written as addition of two vectors. One is this which I'm pointing here as horizontal component, and one is a vertical component. So as you can see here from the diagram itself, that when these two vectors which we call as components add up, you will get that same V0 resultant vector as a hypotenuse of this triangle. Okay. So we have now two components, vertical V0 sine theta 0, horizontal V0 cos theta 0. And one more thing you have to remember is it is this component V0 sine theta 0 that will be affected by gravity. because gravity is in the same, let's say, having the same direction, opposite direction, but not orthogonal, but it's in the same line as this v0 sine theta 0. So gravity will affect this. However, gravity being a vertical downward, it doesn't affect a velocity which is on the horizontal direction. So if you see v0 cos theta 0 has a direction towards right in a horizontal direction. A horizontal, so so it's totally orthogonal to gravity, hence gravity will have no effect on the horizontal component of this velocity because gravity is orthogonal to that component. Okay. Now what do we need to find out in this example? We need to find out when the object will fall. So after how much distance or what will be the range of this object where it will fall back to the ground, and second is what will be the maximum height to which it will reach and at what time it will reach this height. So these three components we'll try to find. So again repeating, we will find out when, how far it will drop back to the ground, what will be its maximum height, and at what time t will it reach this height. Now this time t is calculated basis that the start of the object from its origin will be at time t0. We'll assume that object started from its origin or from where it was thrown up at a time t0. So our reference for time is 0 at the point it is thrown up, and then according to that we will find after how much time t will it reach to the top of the trajectory. Okay, so here we will be applying normal straight line motion formulas because if you see this vertical component, it is totally pointing in upward direction, it is being impacted by a downward direction of gravity, so it's as good as saying that it's like a motion in a straight line but in the vertical direction. Okay, similarly in the horizontal direction we have this force, which we have this velocity which remains constant. So a simple law of motion will be applied to the horizontal velocity. Now let's look at the formulas or derivation for this projectile motion. So as I said, x-axis component is v0 cos theta, the same. Y-axis component is affected by, so I'm talking about this line just to make it clear, this line. So two formulas, one is I already mentioned this, the second formula is this. It is about y component of velocity, and as you know it's affected by gravity. We are using the standard formula of straight line motion, which is v is equal to initial velocity plus acceleration into t. Now since acceleration is in the direction opposite to our velocity of the object in the vertical direction, so hence we use the sign negative with gravity here. Okay. Now using these simple formulas, we will try to find the time when it reaches maximum height. So time when it reaches maximum height is when Vy is 0. If you look at the diagram above, at the top naturally the vertical velocity will become 0 because earlier object was going up. It stops here and starts coming down, right? So at the top vertical velocity becomes 0. Therefore, we will simply use the same formula and we will make the vertical velocity 0, and using that we get the value of this parameter time, and that comes to this. So this is the time after t0 at which object will reach the highest point where vertical velocity will become 0. This is half the path, as you can see from geometry of the projectile at the top. So total time of flight by the time, if you see the above diagram, by the time it reaches here, it will be twice the time it took to reach here. It's a symmetric diagram, and this time will be twice. Of course, this can be calculated mathematically. Now let's find what will be the maximum height to which it will reach. Again, we'll use the law of straight line motion, the formulas of straight line motion. As you know, Vy was in this direction, it was being countered by gravity, so we'll use the relevant formula here. So we will use this formula, which gives us the height of an object at any point, of projectile object at any point. So here we know in the formula it's v0 is initial velocity. Now this v0 is actually, if you look at the figure at the top, this v0 is the initial velocity with which the vertical velocity of the object when it was thrown in at the origin, right? At this point it was thrown, and at that time the initial velocity was v0 sine theta 0. So this we will use in this, so we know this value, it's v0 sine theta 0 actually, not v0, and a we already know is minus gravity, and t we already know from here. We will put this value of t here and also here. So using this formula we will get the value of y at the time tm, which we calculated, and with that you will get the highest point that this object will reach is hm, and this is the value. You have to remember, it's better to remember, of course you can derive as I showed you. So just to repeat, we used this formula of straight line motion where initial velocity going towards in the upward direction in y direction was v0 sine theta 0, as we already have in the diagram above this value, and time here is to be applied is the time when object will reach its highest point, and this we have already calculated here. And acceleration, as I said, we already know is minus gravity, so simply apply and you will get the value of y at the highest point, and that is given here. Highest point is this value. Simply remember this for quick calculation during your competitive exams. Okay, then since we know the time t when it reaches the highest point, and since we also deduced that total time of flight is twice of this, so as you know, just pointing it again in the above diagram here, this diagram, uh, so the time it took to reach this point is half the time it will take to reach the final point. So if you know this point, if you know the time at this point, we will multiply it by 2 and we will get the time when it reaches this point. Okay, so so basically saying the time to reach to for the object to come back to the ground is twice this point time. Okay, and therefore the horizontal range of projectile will be velocity into this time, right? And velocity in the horizontal direction always remain constant. Let's come back to the figure. Velocity in the horizontal direction always remain constant into 2 times Tm. Tm was the time it reached the highest point here. Will give you the range or the total distance, horizontal distance, range of the projectile. So basically, again repeating, so we know this velocity multiplied by twice the time it took to reach here, twice of this time it took to reach here, so then you get the range. Simple application formula, and that is what is given here. Again, you can remember this formula, horizontal range, using the logic I just now explained, you will get this value. So this r means the horizontal distance, this is that r, right? This is r, this is hm, and this is time tm. to reach the maximum height, and this r is the range to reach the final point where it will land back. Okay, it's good to remember these formulas. Okay, now you know that the range or the maximum distance away from a region at which the object will come back is this value. Okay, now if you want the projectile or the object to reach a maximum distance from the origin, so looking at this formula, you can see that if sine 2 theta became 1, which is the highest value that sine 2 theta can reach, then you will have the range as maximum. Basically, maximum range will be V0 square by G, and if sine theta is 1. Now sine theta, let's say, in this case it's sine 2 theta. That means sine becomes 1 when angle is equal to 90 degrees, which means this sine will become 1 when its angle is 90 degrees. That means this 2 theta is 90 degrees. That means theta is 45 degrees. So if you project the projectile at 45 degrees, if this theta 0, coming back to this diagram at the top, if this theta 0 becomes 45 degrees, then this projectile will reach the maximum distance. It will reach the maximum, it will drop at the maximum distance away from origin. So this is what it means. And that maximum distance is given below. That maximum distance is given below, and that is this value. That means sine 2 theta becomes equal to 1. Okay, this is the maximum range. Just remember these formulas, it will be very good for you. This formula, this formula, this formula, and this formula. Of course, don't forget the concept that you can break them into two equations, break them into two velocities. These two velocities as given. This is the important concept, and of course, you will always remember the formulas to use wherever you require. These standard straight line motion formulas are what you are going to use in deriving these values. Okay. In this slide, we will cover a topic, uniform circular motion, as is given in the title. Both uniform and circular words are important here. Now, circular is clear. It is movement around the perimeter of a circle. So if you see what I am pointing out here is an object is moving in a circle like this, and its speed along the periphery or along the circumference of the circle is constant. So that is why it's called uniform. Uniform means speed around the peripheral, around the circumference of the circle of the object is constant. Okay. So this is uniform circular. Now there are some basic geometrical formula which are important here, and I'm underlining that line here. This is what we are going to talk about. First is angular velocity. Now from the very word you can understand it is rate of change of angle with time, and that is what it is directly. So if you see the formula here, it is change of angle delta theta by change of time or the time taken for that change delta t. So clear and simple formula. Then velocity. Velocity, as I said, or let's say the speed here, let's look at it more as a speed. If you look at the diagram on the right hand side, look at this point and this point of the object. These are the points over which the object will pass. This is, let's say, point 1, this is point 2. Now velocity has both direction and magnitude. So velocity at this time, it is in the direction shown. You can see the arrow. And you can imagine when the object reaches point 2, the direction of the velocity has changed. That's why I marked this velocity as v dash and not v. Magnitude has remained the same. Now let's look at the magnitude of the velocity, which we also call as the speed. Now going back towards the left, so speed of the object is distance covered by time taken. So delta s is distance covered or the segment. Now in a circle, we call the distance as a segment. Let me show it to you again. If you see this figure on the right hand side, this portion of travel from point, let's say 1 to let's say point 2 on the circumference, this movement is called a segment. And that segment is over an angle of theta, if you see here. This is the angle theta. So this is the distance a, let's say the object has moved, and if we know the time it has taken for this object to move this distance, so we can get the speed, which is given here on the left hand side, distance covered delta s or the segment, and the time it takes. So it's the speed of the object as it circulates on that circumference. Now, I mentioned two words, which is segment and it is over an angle. So again, looking back at this diagram, there is an angle theta here, and that is covered by a segment S, as you can see here. So there is a relationship between angle theta, let's say in radians, and this distance S or the segment. Now this relation is defined here, which I'm pointing with this arrow. So segment length is radius into the angle. This is what this equation means. Segment length is radius into the angle. And why it's written delta here, for example, for a small change in angle, the distance covered will be this small segment. So this is the relation between segment and the angle in radians. Now, as per definition, angle for a full circle is 2 pi. This is called 2 pi. 2 pi radians. The angle for a full circle, that means looking again at the diagram on the right hand side. So what I am showing you here is, if I start from here, go all the way and go on counting the angle and come back to this point, I would have covered an angle of 2 pi radians. That is what this means. And in that case, using this same, if just looking at this line again, using this same formula, the full circumference of the circle, if you see here as given here, is 2 pi r, using the same formula. So let me simplify it here. What I say is, since the angle of a full circle is 2 pi radians, if you apply this to this formula and multiply by r, you will get the full circumference, and that is what is given here. Okay. Now going forward, we are talking about motion, so we'll be talking about speed along the circumference. We'll be talking about something called acceleration also. Now let me tell you, coming back to this diagram, please understand that this was this velocity and its magnitude remained the same, but its direction changed. So you can imagine that an object going in this direction earlier, and now it will be going in this direction. So that means there is some sort of a force or an acceleration which is turning the direction of velocity from this to this, right? So there is some acceleration. This acceleration, this acceleration, which is this direction towards towards the center of the circle. This acceleration is towards the center of the circle. That's why it's called centripetal centripetal acceleration, and that is defined by a formula. So good to remember this for quickly answering your competitive exam questions. So this accelerations, AC centripetal acceleration, is also defined by v square by r, that's the speed square by radius, or also angular velocity square into r. Okay, just remember this. Also, this velocity along the, or the speed around the circumference, can also be written as r omega. R into angular velocity will give you the speed of the object as it moves around the circumference. Okay, then now you can write these same formulas in a different form using something called time period or frequency. Now let me define what is time period or frequency. To make it easier, just remember these formulas. Derivation you can always read in your NCERT books, but then for practical use of these formulas in life or even for your competitive level exam, you just need to remember these formulas to use them and understand them well. That's most important. Okay, so what is frequency and what is time period? Some definitions given here. Now, time period is the time to cover full rotation of the circle. So again, looking at the figure on the right hand side, object, let's say, starts from here, it goes all the way here and comes back here. The time it takes is time t. So this is what is given in this line. Now, frequency is how frequently the object rotates in 1 second. This is what is the meaning of frequency. How frequently the object can rotate in 1 second. So that means in 1 second, how many times the object can go around. This is what is called the frequency. Now we know that one round is made in t seconds. So therefore, in t seconds. So therefore, in 1 second, how many rounds he will make is 1 by t, right? So you can think over it. You can stop the video, think over it. So frequency is 1 by t. That is why 1 second by t seconds is frequency. This is frequency is denoted by such a symbol. Actually, you will see this symbol below here. For example, here is this symbol, here is this symbol, and here is this symbol. Okay, this is frequency. Now, representing the equations above, representing the equations, all these equations above, we will rewrite in form of the term frequency, and it's again, you can remember these formulas. So first, angular velocity is represented by this 2 pi into frequency. Velocity or speed at any point is represented 2 pi r into frequency, and centripetal acceleration or acceleration towards the center of the circle is represented by 4 pi square frequency square into radius. R is the radius. 2 pi we know is actually the full angle in radians for a full circle, just to give context to these formulas. So 2 pi is actually full angle for the circle in radians. This is frequency and r is the radius of the circle. So now questions could come that you are given frequency and you need to find angular velocity or speed or acceleration, or in some other cases you are given angular velocity and you need to find the speed of the object at any point or velocity of the object at any, the magnitude of velocity, r being given, the radius being given, and so on. Or you're given angular velocity, radius, and you need to find the centripetal acceleration. So this is how you will simply solve these questions. Many straightforward questions could be there. Okay. Now, this is a question from NCERT book, question number 4.13. Though it's a very simple question, but it's good to remind us of a few concepts related to velocity. Now, let's look at the question first, and I'm highlighting it here. A man can swim with a speed of 4 kilometers per hour in still water. How long does it take to cross a river 1 kilometer wide if river flows steadily at 3 kilometers per hour? And he makes his strokes normal to the river current. This is important. So let's analyze the question and draw a diagram. It's always good to draw a diagram and very clear one. It avoids making silly mistakes. So man speed is 4 kilometer per hour. And the other important fact is he makes his strokes normal to the river current. So he's putting his 4 kilometers per hour speed always normal to the flow of the current. And that's, if you look at the diagram that I have drawn here, this is the man and he is making strokes at 4 kilometers per hour, which is normal to the flow. Flow is in this direction. He is making his strokes normal. Okay. Then the next important factor is which is given here is that water is flowing steadily at 3 kilometers per hour. So that means the speed of water is naturally towards the right, and so therefore it is at right angles to how the man is swimming. So the speed of water is towards the right and its speed is 3 kilometers per hour. So let's look at what they're asking. How far down the river does he go when he reaches the other banks? So what they are asking is, so downstream is this. Downstream we know is this, how far down the river they are asking. So what they are asking is when man is swimming like this, normal to the flow, and flow is like this, how far down the stream will he reach the other bank? So that means they are asking you to find out this distance. Man is trying to swim normal, but however stream is taking him down. So they are asking, what they're asking is how far will he slip down and reach the other side? So this is the distance being asked. Now one thing to remember is these two velocities are 90 degrees to each other. Man's velocity is in this direction, stream is in this. So in a way, the stream will not affect the velocity of man, neither man's velocity naturally has any effect on the velocity of the stream. Hence, they are two totally perpendicular to each other and they are not impacting one another. So, what that means is first, now there are two things. If we find out the time man takes to cross the river, and if that time we multiply this velocity with, we will get this distance. That is the strategy that we'll follow. So I repeat, first we try to find out how much time does man take to cross this river, and we know his speed is 4 kilometers per hour, and it's also given that the river width is 1 kilometer. So we can find out, and I'm going to point the formula here. Time to cross the river is river width, which is 1 kilometer. Of course, we have to take care of the units, divided by speed of man is 4 kilometers per hour, but you have to convert these into meters per second if you want it in seconds. So, or you can keep the units in kilometers and then you get it in minutes. So whichever, but you have to take care that you always use same units all through. So with this, you can find out the time it takes for man to cross the river. Once this time t is known, as we know that velocity of man and velocity of river don't disturb each other in a way. They don't interact with each other, so their speed remains the same. So river speed will continue to be 3 kilometers per hour. So while man is swimming, he will be drifted slowly like this by the stream and he will reach here. And this distance will be the speed of a river, which is 3 kilometers per hour, multiplied by the time that man took, which we calculated. So this will give you this distance. It's a simple question, but just to remember that these two velocities don't disturb one another, don't impact one another, so they will remain as they are and they can be used to calculate your answer. Okay. So let's now move to the next question. Now, it's good to mention that there is another way to solve this problem, which is by a resultant vector method. So we have learned how to add two vectors and find the resultant. We'll use that same simple principle. So we know the question. So let's look at it from a point of view of a resultant vector. So, okay, this is the basic diagram. So there is a vector of man swimming at 4 kilometers per hour velocity, another vector that the river is flowing with 3 kilometers per hour velocity in this direction. So naturally, the resultant of this vector and this vector will be this by simple addition. Now, putting that in a more clear diagram on the left hand side. So this is the diagram I'm talking about. So man, velocity of the man is 4 kilometers, velocity of the river is 3 kilometers per hour. So you add these two vectors by vector addition method by putting the head of this attached to the tail of the next one, and then naturally by geometry itself you get the resultant. This is the resultant vector. That means this is the path that the swimmer will actually make if looking from a stationary object in the air at the top. So if there is a drone at the top or a stationary camera at the top of the river, man will actually be flowing like this towards his destination here. And as you know, what question wants us to do is it wants us to find this distance, right? So now knowing this principle of vector addition and being able to find the resultant like this, we can find out the angle theta that this resultant will make, with the strokes of the man or with the normal swimming of the man. So this is simple, tan theta is given by 3 divided by 4, as simple as that. So tan theta will be given as 3 divided by 4. So we already have this angle. Now let's look at another related diagram. We know that the width of the stream is 1 kilometer. Width of the river is 1 kilometer. We know that man will make an angle, this same angle which we found out here, theta angle, which is inverse of 3.4, and you will get the angle. So this is the angle that man will make. Once we know this angle, we will know where he will hit the other side of the river. It's simply geometry. We know this angle. We know that this is 1 kilometer. So all we have to do is we already know that tan theta is this distance, this unknown distance divided by this. So let's say unknown distance divided by 1 kilometer is tan theta, and that's same as 3 by 4. So this unknown distance can be found out as 3 by 4 kilometers, which is 750 meters. So this is another easy way of doing this question. Okay. Okay. This is another question again from NCERT textbook as given at the top here, and this question is 4.14 question from NCERT textbook. Let's read the question, and as I always say, it's best to draw the diagram around it. So, what does this question say? In a harbor, the wind is blowing at the speed of 72 kilometers per hour, and the flag on the mast of a anchored boat is fluttering along northeast direction. So there is a wind of 72 kilometers per hour, because of which flag is fluttering in the northeast direction. Now look at the diagram here. North compass is shown, north, south, east. The flag is fluttering in the northeast direction. So we can draw wind blowing in this direction as at the speed of 72 kilometers per hour, that is causing the flag to flutter in northeast. So that also means northeast means this is at an angle of 45 degrees with respect to east. That's why it is northeast. Let's look at the next part of the chapter. Okay, now if the boat starts moving at the speed of 51 kilometers per hour towards north, then the question is, what is the direction of the flag on the mast of the boat? So if boat starts moving at the speed of 51 kilometers per hour to the north, so here using a bit of common sense, so boat is moving in the north direction at 51 kilometers per hour. That automatically would imply that flag is facing a wind in the opposite direction. So if boat was stationary and there was no wind, the flag would not face any wind. But if this boat starts moving in the northern direction with 51 kilometers per hour, so that would mean, using common sense, it faces a wind in the opposite direction at 51 kilometers per hour. So that means in the direction of the south. So this is another vector which is impinging on the flag. So it's shown here, this vector is being shown here at 51 kilometers per hour, and that this we call as vector B. So the first is vector A, which is the wind blowing, and second is vector B, which is due to the movement of the boat. Now we have to find the resultant vector, because the question says to find the direction of the flag on the mast of the moving boat. That would of course be resultant of these two vectors, of these two winds impinging on the flag. So we use the method of parallelogram as shown again in this diagram, and here we have put 72 kilometers per hour vector A, which is the wind, and then vector B due to the movement of the boat, so that's 51 kilometers. And using the method of parallelogram, we will try to find out the angle of the flag. Now what we have already been given is vector B is in the south direction, is north to south direction, while vector A is 45 degrees to the east direction. That would in effect mean, if you look at this diagram, this is vector A and this is same direction as vector B, which I am pointing. This is vector A. So this angle would be 45 plus 90. So this is 90, this is 45, because this direction is northeast. Therefore, we can safely say that this angle is 90 plus 45. This is theta. This is in fact the angle between two vectors, between vector A and let's say vector B, because this B can also be written here just to know the angle between the two. So this is theta as per the parallelogram formula that we have used to find resultant. Now looking at the formula that we'll use for this question, which is given here on the left hand side, theta is the angle between the two vectors, so that is 90 plus 45. This we know the value of the two A and B vectors, so we can find out alpha. What is alpha? Alpha is the angle with respect to vector B that flag will flutter for the board. So once you know alpha, you can find out exactly the direction of flutter of the flag with respect to north, south, east, west. So it's a direct application of formula. So let's look at another question here. This is question number 4.30 from your NCERT books, and I'm going to read that and I'm marking it here. Okay, this is the question. So the question says a fighter plane flying horizontally at an altitude of 1.5 kilometers with a speed of 320 kilometers per hour passes overhead an anti-aircraft gun. So what he is asking is at what angle from the vertical, should the gun be fired for the shell with muzzle speed of 600 meters per second to hit the plane? So let's draw a diagram. As I always say, better to draw a very neat diagram. You make less mistakes and it's faster for you. So we have a plane flying at an altitude. So this is the diagram. And we have the plane flying at an altitude of 1.5 kilometers. Its speed is 720 kilometers per hour, which translates to 200 meters per second. It flies over an anti-aircraft gun. As you can see, it flies over an anti-aircraft gun, and anti-aircraft gun fires shell at the speed of 600 meters per second. Now the question is, at what angle should this gun? So he wants to find this angle from the vertical. So let's say this is alpha angle. So he wants to find this angle. At what angle from the vertical should the shell be fired so that it will hit the plane at some point? So it assume that plane will also move forward and it will happen somewhere, for example, here. So this is the question. Okay. So what he has asked us is to find out this alpha. Now, a few things to note that whenever a shell is fired, let's say it's fired with 600 meters per second, it will have a horizontal component and a vertical component of velocity. Now, to hit a plane, the horizontal movement of the shell should coincide with the horizontal movement of the plane. What that means is distance traveled by plane in a certain time should match the distance traveled by the shell in that same time. Then only hit can occur. That is one of the conditions. So shell moves like this and assume it hits here. It hit here because the horizontal movement of the shell was also this distance and horizontal movement of the plane was also the same distance. So we'll use one of the formulas that we will use is using this logic, this particular logic. So let's look at that equation. So I'm pointing to that equation now. So we know speed of the plane is 200 meters per second. Assume it travels at some distance in time t. In the same time t as we have said, the horizontal movement of the shell should also cover the same distance. So horizontal speed of the shell is 600 cos theta. Let's look at that in the figure. We say this angle is theta. That means what we say is this angle is theta for us. This angle is theta. So if if the shell is fired at 600 meters per second, naturally the horizontal component of that speed will be 600 into cos theta. And this will be constant because there is no acceleration acting on the horizontal component. Hence, this speed will be constant. And that's what we are writing in this equation on the left hand side. That 600 into cos theta into t will be the same distance traveled as that traveled by the plane in the horizontal direction. Now with this equation we directly get the angle of the shell because if we know cos theta we will know the angle. So using this equation we get cos theta is equal to so much, and just to come back to the figure, our interest or the question being asked is, so as I said, we know this is theta, this angle is theta, but what he is asking us is this angle with respect to vertical. I have called this alpha. So alpha will be 90 minus theta, and that's what, if you look at the line below, 90 minus theta is alpha. We need to find out alpha. So using this equation which already gave us cos theta is 1 by 3, and using this equation of alpha 90 minus theta, which means theta is equal to 90 minus alpha, just transposing alpha and theta. So we replace theta here by this 90 minus alpha, and we get this equation, and then we'll find sine alpha 1 by 3, so we can find out the value of alpha using this equation. So it's straightforward. Okay. So this solves the first part of the problem. The second question in the problem, let's look at the problem at the top again. So what is the last line telling us? It asks us at what minimum altitude should the pilot fly plane to avoid being hit. Now we already know this, let's say angle theta. We already know this angle theta. So we know the maximum height that this shell can reach. It will take a trajectory something like this. So we already know what is the highest point that this shell can reach. We already have formulas of projectile, standard formula. So just apply that formula. You know theta, you know V0, which is 600 meters per second. So you will get this value directly. So the other part of the problem is simple. Okay. One fact is very clear from this question and based on the calculation that we did earlier, that the angle at which shell should be fired should be such that horizontal speed of the shell, again repeating, horizontal speed of the shell should match that of the aircraft. That's a clear deduction. Okay, let's move to the next slide. This is another question from the same chapter. However, this is taken out of NCERT exemplar book, and the question there is 4.24. Let's look at the question which is given at the top here also. So what does the question say? A fighter plane is flying horizontally at an altitude of 1.5 kilometers with a speed of 720 kilometers per hour. So, okay, let's draw this diagram and then we'll continue writing the question. So, as I always say, draw a clear and big enough diagram so that you don't clutter it. So, here in this diagram, which I pointed, we have a plane here which is traveling at 720 kilometers per hour, which is equal to 200 meters per second. That is its horizontal velocity. The height of this plane is from Earth is 1500 meters, so 1.50 kilometer, which turns out to be 1500 meters. This is what is given in the first part of the question. Now the next sentence says, at what angle of sight with respect to horizontal when the target is seen should the pilot drop the bomb in order to attack the target. So he wants to know at what angle of sight when the target is seen. So this is the plane in the diagram, and this is the target, let's say. So they say at what angle should the target be, that this theta, this angle theta. At what angle should the target be with respect to the pilot? So that's what he's saying. At what angle of sight should the target be seen with respect to the pilot? So this angle theta. When if pilot drops the bomb, it will hit the target. So let's assume that angle is theta. And as I've written here, this angle is theta. Okay, and so this is the bomb which pilot will drop. Once he sees the target at an angle theta, he drops the bomb and it should hit the target. That is what is the aim. Now, a few things are known. We know the horizontal speed of the bomb will be same as that of the aircraft, and that will remain always constant at 200 meters per second because gravity doesn't act on this speed. This is a horizontal speed, and gravity is in the vertical downward direction, and orthogonal vectors don't interact on one another. Okay, so uh, pilot drops the bomb at this point, and what will happen to the bomb? It has to travel a distance of 1.5 kilometer or 500 meters, and we need to find the time in how much this distance will be traveled. First, let's find out the time. So let's look at the equation that can be applied here. So look at this equation which I'm trying to point in one of the lines. X is equal to V0 t plus half a t square. Now X is known. The distance to travel by the bomb is 1.5 kilometers or 1500 meters. V0, the bombs, and this is all about vertical motion. We are applying this formula for vertical motion, for the bomb to fall downwards, only for the vertical motion, not for the horizontal motion, because this we are dealing only with the vertical motion. Okay, so this formula is for the vertical motion, and we know x is in the vertical direction. It has to travel a distance of 1.5 kilometers to reach the target. Initial velocity in the vertical direction was 0 because bomb started from a 0 velocity at the top. However, its speed will go on increasing because of acceleration, which is gravity. So let's use this formula to find the time it takes for the bomb to reach the ground. So the only unknown in this now is t. So as I said, vertical velocity of the bomb was 0, hence this equation just reduces to x equal to half a t square. X we know is 1.5 kilometers. A we know is the gravity, and we just need to find t. Now using this formula, we find that t is 10 root 3 seconds. So let me, okay, so we know the time it will take for the bomb to reach the target. In this time, let's find out what will be the horizontal distance covered by the bomb. Now, horizontal distance covered by the bomb in time t will be velocity into time. Velocity we know of the bomb is 200 because it's the speed of the plane, and that won't change because of gravity because that is in the horizontal direction. So 200 into time we already found out 10 root 3. So we get the distance, horizontal distance that bomb will travel. So let's do a bit of geometry here. In the right lower diagram which I am pointing here, this is the distance, horizontal distance that bomb moves, 200 root 3, which we calculated here. This we have brought it here. This we know, right? And the vertical distance that bomb moved was, vertical distance we know was 1.5 kilometers, and this is 500 meters. Hence we know the base of the triangle, we know the height of the triangle, so we can find out the angle at which the pilot should see the target. So this angle, if we find out, which I'm pointing here, is same as this angle with respect to horizontal, and this is the angle that we had started to find out for the pilot. At what angle should he see the target, that he should drop the bomb at that point. So it's basic application of geometry to get you the answer. So tan theta will be 1500 divided by 200 root 3, and that will give you the angle. Okay, let's look at the last question here. This is from NCERT exemplar book, and the question number is 4.32 there. So this is our question at the top again. So what does it say? A particle falling vertically from a height hits a plane surface inclined to the horizontal at an angle of theta. So again, making a diagram, if you see this particular diagram, you see a plane which is inclined at an angle of theta, and a particle is falling vertically from a height. So this is that particle which is falling vertically from a height on the plane. So vertical means vertical to the earth, or this surface at the bottom. It's vertical to this, not vertical to the plane, but vertical to the ground. Okay, next. What does the next line tell us? So, okay, it falls with a speed of v0 and rebounds elastically. This is important to understand what this means. So, this is our article which is falling with a speed of v0 and rebounds elastically. Elastically means it will come back with the same speed. So, if this is hitting with v0, it will move out also with V0. This is what elastic means. And secondly, the other point to remember is if you draw so this is the plane on which the ball or the particle is falling, and this is the perpendicular to that plane. This line is perpendicular. Now the angle that this body will make with the perpendicular to the plane on which it is falling, the same angle will be made by when it rebounds back. So when it rebounds back, it will make the same plane and same velocity v0. If it falls with v0 here and an angle, let's say alpha, it will again make an angle alpha here when it rebounds back with the normal of the surface. So this is what is elastic rebound. Okay. What the question asks us to find, and I read the question, find the distance along the plane where it will hit the second time. Okay, so it's basically acting like a projectile. Coming back to our diagram, so particle starts from here like a projectile with v0 velocity at an angle, and we need to find out when will it hit back the plane. So we need to find this distance. This distance we need to find after how much time will it hit back the plane. So in this case, we will follow a slightly different approach, though principles will all be the same. But what we are going to do is we are going to make our origin as this point where the object flies out like a projectile with a velocity v0. And that's normal. We always assume this as a starting point in all our calculation, even with the normal projectile. The only difference is it is starting from a plane here. But anyway, we can fix our axis wherever we like to make it convenient for calculation. So we have fixed our origin here, and we have fixed our x-axis as this one, and we have fixed our y-axis as this one. So this is our lines of reference. X-axis is this, y-axis is this, and this is our center. Okay. Now, let's look at it one by one. Now, look at the vertical motion. Vertical means vertical with respect to this plane. A few things to get from geometry. Look at this figure below. We know that this object is falling with a angle, let us say theta. Let's assume this is okay. Okay, not. Let me make it the other way around. The object is falling vertically. Vertically means with respect to ground, it is vertical. However, it is falling on a plane, not on the ground, and this plane is at an angle of theta. We know that given by the problem itself. Now, if we draw a triangle here, if we look at it as a triangle, this part which is below the plane, we see that it has an angle theta. We know that it is falling vertically, so this is at 90 degrees. So naturally this angle is 90 minus theta as also given here. So you see it's already given that this angle is 90 minus theta. Now an angle opposite to it, which is here, is also 90 minus theta by simple trigonometry. Now this is 90 minus theta. Which is this angle? We know this object is falling from the top, right? This object is falling from the top, and it is therefore falling at an angle of 90 minus theta, and this side. On this side, the angle is 90 minus theta. We know this is perpendicular to the plane. This line is perpendicular to the plane, and since this is 90 minus theta, and this angle is also theta. Okay, so we have now deduced that this angle is theta. Now, we know that this is an elastic rebound. So the angle that this object will make with the plane, with the inclined plane, with the normal of the inclined plane, it will rebound back with the same angle theta. That is why this angle is also theta. The second angle is also theta with which it will rebound back. So now for a projectile, for to apply our equations, we generally are more interested in the angle that the projectile will make with our reference plane or this plane, let's say. So this will be 90 minus theta. Since we already found out this is theta, and we know that this is the perpendicular to the plane, so this will become 90 minus theta. So the angle with which the object will fly out of the plane will be 90 minus theta with respect to the plane. Okay, and this is what is given here. This angle is 90 minus theta. Therefore, looking at this diagram now, this is for the v0 vector. So the object is flying back with velocity v0, and its angle is 90 minus theta with respect to this plane. Therefore, its horizontal and vertical component with respect to the plane. Remember, we have changed our axis to this as the origin, and this is x-axis and this is y-axis. So ours is, our frames of reference are slightly different than the normal projectile. So now we know this is the velocity, so horizontal will be this, as vertical component is this, horizontal is this. Horizontal is V0 sine theta and vertical will be V0 cos theta by simple application of geometry. Okay, so we know these two components, vertical component with respect to plane and along the plane. Similarly, we will find out vertical and horizontal components with respect to plane for acceleration, which is gravity. So if you look at this figure below, the only other acceleration falling on this ball is gravity. And this gravity is downwards, vertically downwards. However, plane is inclined at theta. Therefore, its component on perpendicular to the plane will be minus g cos theta because it is in the negative direction of our axis, this being the positive direction, this being the negative direction. So this will be minus g cos theta, and the component along the plane will be g sine theta because we know this angle as 90 minus theta. Okay, because this angle is same as this angle. So this is 90 minus theta. So the component along will be g sine. Now it will not be negative because it is in the same direction. It is in the positive x direction of the axis of our frame of axis, and it is in the same direction as this component v0 sine theta. So we'll be adding these two in case we want to find a distance here. Now, which formula to apply? Now we have two components, horizontal and vertical. We have two components, horizontal and vertical, of acceleration. So there is acceleration also in the vertical plane and horizontal plane, and there is a velocity, initial velocity. Now we and our okay, so okay, we have the two components. Let's find out first the time it takes for ball to travel from this point to this point. Now, time can be found out if we know this path and we try to find out when the vertical component or the vertical distance traveled will become 0. So it starts from this point, it goes up and then comes back to the same y point or the same point on this y-axis. Suppose this is y-axis, it goes up here and then comes back here. So we want to find out when y becomes 0 for this object again. Okay. So if you remember from formula for straight line, motion in a straight line, if you see this which I am pointing on the left hand side, this is the formula for motion in a straight line. In this case, it is the vertical direction. Now we want to know when y will become 0 again. So, and which are the other parameters that we know in this equation? We know the initial velocity v0, that is, if you see on the right, this velocity v0 is v0 cos theta is the perpendicular component of velocity, initial velocity. We know acceleration, it's not g purely, but it is, if you see the vertical component of acceleration, it is minus g cos theta, right? On the right hand side, if you see minus g cos theta. Therefore, applying what we know, we simply have to put v0 cos theta as the initial velocity into time and minus g cos theta as the component of acceleration. And therefore, with this, and assuming y will be 0 when ball falls back, we will find that time for ball to travel back to the plane will be 2v0 by g, 2 initial velocity by gravity. So this is the calculation. Now, once we know this, we have to find the horizontal. Now look at the diagram again. We have to find the horizontal distance that this object will travel, right? And that can be known if we know the velocity along this plane and apply a formula related to that plane. Now here again, since there is acceleration, we simply cannot say velocity into time, but we need a formula which takes into account acceleration as well. So the formula which for a motion in a straight line that includes acceleration is again the same one here. Sorry, I come back to the same formula. This is the same formula except that for instead of y we will use x and we'll fill the different parameters. Now let's see. So look at this formula, which is same formula applied for motion along the plane. So x is the distance along the plane that we need to find out how far the object will go before it hits back the plane. So this x is something we need to know. And what else we know? We know time because time was calculated here. So time is known. We know the initial horizontal velocity of the object, and let me show that to you again in the diagram. We know this was the initial horizontal velocity, so we know v0. We know, coming back to the formula, we know that acceleration is g sine theta. How did we know this? Look at the diagram here. We know along the axis g sine theta is the acceleration, so we know acceleration. We know time from this formula. We know everything. We can find out x. So by simply applying these values in this equation, you will get the equation of the distance traveled or the range of the object on this plane, which is this distance, is what we are interested in. Okay. So this completes the chapter. With this, you are reinforced to be able to solve almost any problem, even more difficult ones in competition. But practice makes a man perfect. So practice problems from competitive exams. All the best.